morning. This is going to be a very short series of lectures on inverse function theorem. And throughout my career, I found that students across the country, even some across the world, have problems with this. The proof you find in textbooks are very terse, and the way it starts, it's a theorem and a proof and in by itself. But most important than the proof, what one has to learn is how to use it, why it's important, what is its significance. So the first few minutes of my talk will be to kind of set the stage so that you will begin to appreciate what the theorem is about. Okay, and then we will start with this precise statement of the theorem and get into the proof. So it will require more than one lecture, possibly two. Let us see. Okay, are you ready? Okay, let's get go ahead. Okay, the references are given already. Okay, the proof which I follow will be essentially in my book on differential geometry and Lie groups, also a forthcoming book, and partly I will also be following Apostle to give some proof. Okay, we will come to that, don't worry. Okay, yeah, now let's try to understand what it is. See, mathematicians understand given two objects, they may look different, but they realize they are the same in some sense. The labeling may be different. Okay, what do we mean by that? For example, just for fun, let us say I denote by Z3 and I also look at A, B, C. Okay, then if I set up a corresponding 0 to A, and that is what if you want one bar to B and 2 bar to C, then I can define a cyclic group structure on ABC. Right, that is A plus B equal to B and A plus C equal to C and B plus C, that is 2 plus 3, that must be A, and so on. You understand that? So I can define all such structures. And what will be B plus B? B plus B will be C, whereas C plus C will be, that is 2 plus 2, therefore it will be A. You understand that? So I can also define A, B, C satisfying this kind of binary. I might have left few of things, but they are one and the same. That's where you look at the isomorphism concept, right, in of groups. Okay, so when it's given two sets X and Y, okay, when you set a bijection, it's just a sets. Okay, what do I get is I'm labeling them in a different way. That's it. Okay, whatever is X, I call it Fx now. That's it. Right? Like 0 is A for me, your 1 bar is B for me, your 2 bar is C for me, like that. So you are just labeling. You follow that? Okay. So there is no, distinction once you identify these objects this way. But the moment X and Y has more structure, like suppose X and Y are groups, okay, then what do I need is F is not only a bijection but also it preserves the operations. That is, I want it to be a homomorphism, and since F is a bijection, I also want F inverse to be a homomorphism. That is F from X to Y and F inverse from Y to X, both should be homomorphism. But this is gratis, this is free, you get it free. The moment F is a bijection, F is a group homomorphism from X to Y, F inverse is automatically a group homomorphism. Alright, and similarly, suppose X and Y are vector spaces, you have a similar thing. F is a bijection, then what do I need is F is a linear map. Then, and I also want F inverse linear map, but again this is free. Once it's a bijection linear, then F inverse makes sense, then F inverse from Y to X will be automatically linear. Alright, but on the other hand, if I have a topological space, I hope all of you have some idea about topological space. Okay, then F is of course a bijection, but then what do I want is F and F inverse both should be continuous maps. Okay, f must be continuous as well as f inverse is continuous. F is from x to y, f inverse is from y to x. See here, this is not free. I have to insist. Okay, so in algebra usually isomorphism, you just to say f is a bijection, f is some kind of a homomorphism. Finished. That's enough for you. Okay, you don't insist that f inverse is a homomorphism, because it comes automatically. But in general, that's not the case. So you want it to be both ways, that f as well as f inverse should be some kind of a homomorphism. Homomorphism meaning whatever is the relevant map between the objects with the additional structure. Okay, keep that in mind. Okay, now I'm going to ask you a question. Suppose my U is an open set in Rn, and V, then you say this is a homeomorphism. This is an isomorphism among topological spaces. And suppose V is also an open set in Rn, and what do I want is, I want U to be a bijection. Okay, but remember, we are talking about differential calculus. Okay, differential maps, etc. So what kind of an isomorphism I should look for? What kind of isomorphism I should look for? So an obvious guess, all of you I'm sure would have said, is f. See, remember, f and f is a map from U to V, U and where both are open sets. Okay, both are open, and f is a bijection. Therefore f and f inverse makes sense. Very good. Now what is the isomorphism you should look for? Because remember, I am looking at differentiability. Therefore the obvious guess for you would be f and f inverse both are differentiable. Okay, that is the kind of isomorphism you may want. Okay, do you think this is very natural? Yeah, based on whatever you learned, that's very natural. But for technical reasons, we do not want only f and f inverse. What we want is slightly stronger. Okay, the isomorphism here is called a diffeomorphism. Okay, what is it? I say a map F from notation as above is a diffeomorphism. I say it's a C1 diffeomorphism. F from U to V is a C1, and f inverse from B to U is a C1, and this is a bijection. So when do I say it's a C1 diffeomorphism? First of all, it must be a bijection, and the map f and f inverse both must be C1. Just quickly recall, if I write f equal to f1 to fn, then each fi is a linear map from U to R. So when do I say this is C1? I say it's C1 if all the partial derivatives dou f by dou xj exist and are continuous. Therefore, when I say f is C1, I want each f1, f2, fn must be C1. And similarly for f inverse will be from B to R. Okay. More generally, I can define what is called a CK diffeomorphism. Suppose K is any natural number, I say CK diffeomorphism. Can you guess what should be the condition? Yeah, f must be a bijection, and f from U to V must be a CK map. And since f inverse also makes sense, f inverse as a map from B to U, that function should also be CK. What is the meaning? Each of the components function fi should be CK. What is the meaning? All partial derivatives up to order k exist and are continuous. I'm sure all of you have seen it already when we discussed Taylor's theorem, etc. Okay, have you understood so far? Please quickly pause, review, and proceed. Okay, so inverse mapping theorem talks about a diffeomorphism concept when two sets are likely to be diffeomorphic. Open sets, of course. Okay, and we will restrict ourselves to C1. Later I will indicate how one can extend the result to CK also. Okay, right, this is one aspect. Okay, right. There is other aspect. The other aspect is, let us look at vector space B, and suppose I have a linear map T or f if you want, okay, from v to v. So assume these are all finite dimensional. Okay, now if I give an ordered basis v1 to vn, assume n dimensional, then I can write matrix of T will be something AIG. Okay, let's not worry about how it's done. It is done, right? Then what do you do there? You the so-called canonical forms, etc., choose a basis v1 v2 vn so that you can represent T in a somewhat simpler fashion. For example, suppose this is an eigen basis. Okay, that means C of vi equal to lambda I vi for all I. Okay, it may not exist, but suppose it exists. Okay, then any basis gives rise to a coordinate system. Any vector v, okay, vector x in x, I can write as summation xi vi. Now I am assuming it's an eigen basis, right? Therefore, writing T, choosing this eigen basis, it makes my life simple. Tx is nothing other than lambda, right? X equal to x1 to xn. Then Tx will be just lambda 1 x1, lambda I and xn, or if you want in terms of basis, lambda I xi vi. Yeah, you understand that? So changing this a basis gives rise to another system of coordinates, and with respect to that system of coordinates, I can understand the function, the linear function T well. Do you follow that? Yeah, for example, okay, I don't want to spend such time, then you should go to linear algebra lectures, you will see that. Okay, so keep that in mind. Okay, so change of basis gives a new system of coordinates, right? Each basis, ordered basis of course, correspond to system of coordinates. Okay, right? Change of basis means I am changing the system of coordinates. You follow that? So this system of coordinates, one usually say linear change. Linear change of coordinates, because I am using it by linearly. Okay, you understand that? The original vector x, suppose with respect to some other basis, something like yj wj, then this yj and xj may be related. In one of my lectures on linear algebra, I had explained how I can do that. Okay, remember, so just keep that in mind. Mathematics is fun if you try to relate all these things well, so that you see it's the same pattern, same question. Depending on the context, we get the correct answer. Okay, the question may have to be slightly modified, and we should aim for a better answer. Okay, so change of basis is same as saying I am ready to change linear change of coordinates. What inverse function theorem says is it talks about non-linear change of coordinates. Okay, this is what inverse function theorem talks about. What does it mean? Let me ask you a question. Suppose I am an R2, okay, plane Euclidean plane, or if you want R3, right, and I have a force, okay, which acts on various particle. Okay, but the force, okay, force is located, let's say, at the origin, and it acts on this. Okay, this is a force. Okay, it acts on this particle. Okay, but the action depends only on how the distance between these two. Yeah, right. Then what kind of coordinates I would like to use? Or let us say another situation. Okay, I have again a system of coordinates. Now there is a force or angular momentum, or okay, a periodical thing. If I have, suppose I have, it depends only on the angle it's subtend to this axis. Okay, then what kind of system of coordinates I will use? I will use polar coordinates. You understand that? Okay, that because my life will be easier, I can explicitly say, right? So remember, then how do I get a polar coordinates? My r is going to be x squared plus y squared to the power half, and similarly theta, tan theta will be y by x whenever it makes sense. Okay, let's not worry too much about such things. Okay, and you can see that they are not linear change. That is, you don't get this coordinate r by a linear change of the coordinates x and y. You are squaring them, adding them, and taking a square root. And similarly, the theta coordinate, I am going to get tan by y by x. It's again not linear. You are just quotienting, okay, assuming x not is 0, and then you are using a transcendental function tan to get a theta. Do you understand these things? Please do not get too much perturbed. Just try to feel what I am trying to say. Okay. So depending upon the situation, instead of the usual Cartesian coordinates xy, I would like to change into polar coordinates. In R3, spherical polar coordinates, or sometimes even cylindrical coordinates. You see that? So these are all non-linear change of coordinates. What inverse function theorem talks about is change of coordinates, non-linear change of coordinates. That is, I will briefly say what it is, okay, with a little more so that you will have an idea. Suppose I have set u in Rn with standard coordinates. Therefore, any point P, okay, I have coordinates x1 of P, xn of P. Okay, that is what my P is. Right. What I may do is I may choose the same P. I will choose another system of coordinates yn of P and yn of P. For example, here xy, I wrote it as r cos theta or sin theta kind of thing, right? So my okay, therefore my x1 is going to be a function of y1 to yn, and xn is going to be a function of y1 to yn, or other way around. Y1 is a function of x1 to xn. For example, here x is a function of r and theta. You follow that? Yeah. And whereas r is a function of x and y, theta is also a function of x and y, and something more also. It's a function. Okay, you follow that? Yeah. So the transition from going the coordinate x coordinate to y coordinates or the other way around is non-linear. Okay, for some reason, instead of using these standard coordinates, rectangular system of coordinates in Rn, okay, I may be happy with the new system of coordinates. Okay, keep this in mind. Okay, please pause, review and proceed. Don't try to be too precise. Okay, don't worry, just try to see, have the feeling, the correct attitude will make your life easier. Okay, right, the next okay, now let's look at a function f from a subset u in Rn, okay, and let's assume the function is c1, that is continuously differentiable. Yeah, and let's fix a point a in u. Right, now what do we know? The derivative d of a, okay, is essentially an approximation, linear approximation. That is, my fx equal to fa plus d of a acting on x minus a approximately. There is an error. Okay, and this function I am approximately equal to some linear polynomial, assuming it is R. Okay, it's a linear system. You understand that? Okay, this is approximately equal to this. Good. Therefore, the intuition is the behavior of f, the locally around a, is determined by the behavior of the derivative d of a. Remember, derivative d of a is a linear map. Call it a. This is a linear map from Rn to Rn. Yeah. So I expect, okay, local behavior of f around a is determined or predicted, determined by the behavior of a, the derivative. What do I mean by that? What I say is, suppose my a is 1 1, naturally in this case is going to be on 2 also, because both dimensions are the same. Okay, if it's a bijection, okay, so especially if it's 1 1, therefore I want to say f is going to be 1 1 where not on the entire domain u, because derivative is a local approximation. So what should I expect? F must be 1 1 in a small neighborhood around a. That's it. Do you follow that? Yeah. So that's the first thing. So if a 1 1, does it imply locally f is 1 1 around a? around the point A. That's a question, right? The next thing is, suppose if it's 1 1, let's look at, let's say for example on a ball of radius r, f is 1 1 on this, right? Under the same assumption, that is the derivative is 1, map is 1 1. So f is 1 1, not on all of you, but in a small open ball. This is contained in u outputs. Yeah, right. Then what should I expect? Let me look at f of bar. Okay, therefore bar to f of bar, this is a bijection onto. Therefore I can talk about f inverse, right? But I would like to know whether f inverse is differentiable. You understand that? But if I want to talk about f inverse is differentiable, remember in several variable calculus, whenever we talked about differentiability, we insisted the domain should be open. Therefore what should I want? I would like to say this is open. You understand this? If it is open, then I can talk about this to BR. Okay, this is differentiable. Is the question clear? Yeah, right? Okay, so inverse function theorem tries to answer these things. Okay, that's what the theorem is about. Okay, let me just see whether I want to say anything more. Okay, because these are subtle points I wanted to say, so let us do that. So what does inverse function theorem says? And now let's try to make a precise statement. So let u be, u is open subset of Rn, a is in u, and let's assume f from u to Rn is, okay, C1. I don't really require it to be C1 on all of you, but let's not worry about that kind of technicalities. Let us just assume, because in wherever you want to apply, you are going to use this. So let f be a C1, right? What we want is, let us look at, when I wanted to say f is 1 1, what do I wanted? The local behavior. I want it to be, the derivative should be 1 1. But when the derivative is 1 1 from Rn to Rn, then what does it mean? It's a linear map, right? From Rn to Rn. If it is 1 1, it's actually onto. Therefore, the derivative must be an isomorphism. That means it's a non-singular. Okay. Okay. So assume that dfa is invertible or non-singular. These are the assumptions. That's it. Okay. Then what we want to say is that f is locally a C1 diffeomorphism. What does that mean? There is an open set UA contained in U, right? And so that f from UA to f of UA, okay, so that this is open and this is a C1 diffeomorphism. That means it's a bijection. So, and the map f from UA to f of UA is C1 and f of UA is open, therefore f inverse makes sense, and I can talk about the differentiability, and f inverse is differentiable. Do you follow that? Let us write it step by step. This one, usually this is not the way textbooks will write, so let us write it. Okay, the first thing is there exists an open set UA, so that UA contained in UA, of course UA is contained in U, on which f is 1 1 2, f of UA is open. Okay, right? Since f is 1 1, the f of UA is open, therefore f is a bijection from UA to f of UA. Therefore I can talk about f inverse from f of UA to UA is again C1. Okay, and we also know what the derivative should be. Okay, if it is derivative, then you can ask for y in f of UA, then d f inverse this derivative of this at which point? At y. What is it? That should be a linear map from Rn to Rn, right? But remember, y is in UA, and since f maps UA bijectively onto f of UA, there is a unique x, so that y equal to fx, right? Then we want to say, so let us look at fx and its inverse. That means, okay, for each x in UA, dfx is also invertible. Do you understand this? Then only this will make sense. So it already gives an idea how I should restrict my UA. Okay, I have to find UA, right? That's the first point. How to find that? This gives an idea how to do that. Keep this in mind. Okay, I hope I got everything right. There is an open set on which it's 1 and so that the image is open and inverse is C1 and the derivative is automatic. This is the easiest part. Okay, right. So this is the inverse function theorem. Please go through it and make sure this, what does it mean? This only says f from UA is an open set, f of UA is an open set. This is C1 diffeomorphism. So what does it mean? So inverse mapping, inverse function theorem says, under the assumption f is C1 and derivative f at A is non-singular, means then f maps an open set around A diffeomorphically onto an open set containing fa. Yeah? Pause, review, proceed. So now we are ready for the proof. The proof, let us see, there are 3 steps. Okay, and so if the first statement will be 1 step, second statement will be second step, third statement will be third step. That's it. Of which, very interestingly, first and third are somewhat easy and routine in my opinion. Second step is the most subtle step in the proof. That is, the map which has this property, okay, is a open map. Okay, if you have to learn topology, you will understand such things, but anyway I will explain as I go along. So this is the significant, okay, it requires a bit of ideas to do that, whereas 1 and 3 are essentially in some sense routine. Okay, so today I will complete the proof up to 1. Okay, tomorrow we will continue with the second, possibly third also, if time permits. I do not know, that we'll see that. Okay, yeah, okay, now let's start with the proof. So what do I want to prove? I want to prove first step. Step 1 is, okay, to find UA. So that what? F is 1 1 on UA. Okay, at present I will not worry about this. Let us do that. Okay, so when I want to find something is 1 1, let's go back. Even in one variable, if I have something like differentiability, if it's 1 1, and let's assume my n equal to 1, what does it mean? Remember, U is open, right? Therefore it's an open subset in R, therefore it's a disjoint union of open intervals. And suppose I say dfa is invertible, that means that is f dash a essentially, that is non-zero. That means either it's positive or negative. You understand? Therefore if a belongs to an open interval which is contained in U, then I know that f, since f is also C1, that is f dash is continuous, f dash should retain the sign. It cannot change the sign. If it changes the sign, like since it f dash is continuous, by intermediate theorem f dash must vanish at some point. You understand that? So what do I have to do? I have to choose an interval around A so that f dash A is non-zero. Can I do that? Because f is C1, that is continuous, sorry, f dash is continuous, I can find. Please think, I want you to think along with me. Okay, so the first step therefore for this, to do that, Okay, let's go back to R again. Okay, so if I have done that, what it means, therefore f dash A is, let's say f dash A is positive, then I choose a delta interval around A, so that A minus delta to A plus delta is completely contained in U, and so that for every x, f dash x is non-zero. Now f dash is continuous, and suppose f dash A is positive, then f dash x also should be positive. Therefore f dash is positive on the interval A minus delta to A plus delta. That means f must be increasing and strictly increasing. Therefore it's 1 1. Do you understand that? Even in one variable, if you go through the proof, we know what we have to start with. What I have to start with? I have to start with what? An open ball. There I chose A minus delta to A plus delta. You understand? Here I choose an open ball BAR, so that for every x here, dfx is non-zero. What does it mean here? There I said f dash x is non-zero. Here what should I do? My condition is dfa is non-singular. Therefore what should I say? For every x here, dfx is non-singular. Do you understand this? Yeah. So the first choice is, okay, I want to say, do you follow that? Now let's look at dfa. See, let this is equal to dfa, right? Okay, now this is, what do I know? This is in GLNR. Okay, these are set of all invertible n cross n invertible matrices, right? We know this is an open set where in MNR, set of all are real matrices, right? If you want, I can also do something. Okay, since this is non-singular, right? Let's look at then the point x going to determinant of dfx, right? Now what is dfx? Dfx in terms of Jacobian will be del f by del xj at x. Yeah, so these are all continuous functions. You understand that? Therefore determinant is a polynomial. Therefore this is a continuous function on where? From U to R. And what do I know at A? This is non-zero. Therefore what do I know? Since this function is continuous, okay, call this function phi. Therefore phi, okay, there is an R positive, so that on BAR, okay, for all x here, phi of x is non-zero. What does it mean? For all x in BAR, determinant of dfx is non-zero. That means dfx is non-singular. Do you understand the proof? Yeah, guys. Okay, so pause, review, proceed. So this is analogous to what we did here. One variable. Keep that in mind, so you'll really appreciate the proof. Okay, so now I had found an open ball around A, which is of course contained in U, so that the derivative at each point x in the open ball is non-singular. Next, I want to say something like 1 1. Let's go back here. How did I prove in the one variable case? In the one variable case, I said if f dash A is non-zero, for example, assume it's positive, then on A minus delta to A plus delta, f dash is always positive. Therefore f dash is positive on the interval, therefore it is increasing. How did I conclude it's increasing? Yeah, if you have gone through my differentiation lectures, you know. Okay, it's not automatic, by mean value theorem, right? And since it's strictly increasing by, okay, then I know it is 1 1. So essentially to conclude it's 1 1 on the interval A minus delta to A plus delta, what I wanted was mean value theorem. So here also I need a mean value theorem. Yeah, let us do that. So what does mean value theorem said? Okay, mean value theorem said, suppose, now remember BAR is an open convex set, right? So I have this U, I have A, this is an open ball, right? Start with any x1, x2 here in BAR, right? I want to say fx1 is not equal to fx2, x1 not equal to x2, of course. Yeah, now when I want to say what is one result which tells me how to compare fx1 fx2? Mean value theorem. Fx1 minus fx2 minus, I know df of, Okay, I want to say this, okay, right, I want to say this is not equal to 0, right? Okay, now let's recall we proved mean value inequality. Okay, please go through my lecture. What we proved that since x1 and x2 are in the open ball, the line segment joining x1 x2, because this is a convex set, that will lie there. x1 x2 is a line segment that is Canonical BAR, right? Therefore what we found out was there exists, okay, fx1 minus fx2, okay, in norm will be less than or equal to the LUB, that is the supremum for z in the line segment x1 x2 of derivative of fz into norm of x1 minus x2. Okay, so for remember, for any matrix A in M and R, we have the Euclidean norm. Okay, we have a norm with respect to which you are talking about. Okay, therefore this is norm of that. This is essentially Rn squared, so we have a norm using that, but actually it should be operator norm if you know what it means, but let's not worry about it. Okay, this is the theorem which you proved. This is the mean value inequality, right? What we want is an extension of this. Okay, please understand, mean value theorem says about equality in one variable but several variable, the most potent, okay, a useful version is mean value inequality, as I explained in my one of my lectures on several variable calculus. The extension of this is, suppose T is any linear map, okay, this F may be anything to do with U in Rm to Rn. Okay, here I am not assuming this is the same U as we did earlier. Okay, and x1 x2 here, fx1 fx2 may be in R2, etc etc. Let's know. Okay, now suppose T is a linear map from Rm to Rn. Okay, now let us define a map Gx equal to f of x minus Tx. Therefore that G again is a linear map from Rm to Rn, or G from U in Rm to Rn, right? Now let's apply the same mean value inequality for this. G of x1 minus G of x2 should be less than or equal to LUB of derivative of G at z into norm of x1 minus x2, where z varies over the line segment x1 x2. Okay, let's try to understand what is this. What is this object? fx1 minus tx1 minus fx2 minus tx2. Therefore this object is nothing other than fx1 minus fx2 minus t of x1 minus x2. Yeah, that's less than or equal to, what is tg? Remember, G is also differentiable, because if it is differentiable, any linear map is differentiable, therefore this is differentiable. And what is tg? tg of x is dfx minus t. There is no x. Do you remember that? The derivative of this map x going to tx is t. Okay, therefore this object is going to be LUB of z in x1 x2 into norm of dfz minus t into times norm x1 minus x2. Please pause, review. Okay, this is the mean value extension of the mean value inequality which you want to use now, right? Now let's go back to this. Is, as I said, this inequality is for any function f from u from Rm to Rn. Okay, we have proved this inequality for any function from f from u from Rm to Rn, not necessarily the earlier f. Okay, for any f, right? And similarly for any t linear map from Rm to Rn, we have a new function, and with respect to which got it. You understand? Now we want to apply this inequality, okay, to our function f. So we are back to our earlier one. Okay, so what did you do? We found an open ball BAR, so that for all x here dfx is non-singular. Okay, we are back to this situation, right? What I want to claim? I want to claim f is 1 1 on BAR. Not necessarily on BAR, I'm out to restrict. You will see that. Okay, you follow that? Okay, now let us do that. So suppose x1 fx1 equal to fx2, then what do I want to claim? I would like to claim x1 equal to x2, right? Let's look at this inequality. What do I have? Norm of fx1 minus fx2 minus t of, for any, at present I do not know what is my t, but let's equal to LUB of something into x1 minus x2, right? Now look at this carefully. Now this fx1 equal to fx2, therefore what is left with this norm of x1 minus x2 is less than or equal to something. Okay, let us call this constant that depends upon x1 x2, so c times norm of x1 minus x2, right? Yeah, do you understand this? Okay, now let's look at this. So I want to arrive at a contradiction. What kind of contradiction I should arrive at? See, I want this to happen, right? I want to arrive at some contradiction. How will I do that? For simplicity, let's take t equal to identity. Then what do I have on the right left side? x1 minus x2 is less than c times, less than or equal to c times norm of x1 minus x2, right? So if I want a contradiction, that is, or I want to conclude x1 equal to x2, what do you think I should make sure? If my c is less than 1, of course is positive, okay, then I am through. You understand that? So I have to choose a c. I have to ensure my c is such that c is strictly less than 1. Then this will be a contradiction, because norm of x1 minus x2 is some less than norm of x1 minus x2. That's a contradiction. You follow that? And it's less than or equal to, therefore the only way is it has to be 0. Then 0 will be less than or equal to c times 0. That will be all right. Okay, so I have to make sure my c is less than 1. Now what is c? Let's look at c is this fellow. What is that? dfz. What is c? c is LUB of norm of dfz minus t. My t is going to be identity. What? Okay, so what do I want this to be? Okay, this is where we are going to do. Okay, now what do I know is dfz. Okay, remember, where is z? My z is in x1 x2. Where is that? That is in contained in BAR, right? Therefore my z will be close to a. You follow that? So I want to say dfz, because f is c1, dfz will be close to dfa, right? Therefore if I restrict my r very small, then the distance between dfz minus dfa, that is, remember, these are other matrices, we have defined the norm between them, therefore that is dfz minus dfa. I know I can make sure it is less than some epsilon for all z. Okay, choose r so that for all z in BAR this happens. Yeah, but what I have is identity. Here I want a DFA. So what do I do? Okay, let us again okay, for simplicity let us assume DFA is itself is identity. Okay, do not worry, try to understand, learn. Okay, then you go through any of the book, you will see why the proof is so easy. Okay, now I'm thinking aloud, so you will look as though it's very complicated, but but it's not true. Okay, let us assume DFA is invertible, right? Let me assume DFA equal to identity. Then what happens? Since f is c1, there is an r positive, so that the distance, that is norm dfz minus dfa, will be less than epsilon for every z in BAR, right? Now what is BAR? Z, it is on the line segment x1, x2, which is completely contained in BAR. You understand that? Yeah. Therefore, I can make sure I can choose R. Okay. Since F is C1, choose R positive, so that for every x in BAR, norm of dfx minus identity, which is my dfa, is less than half. Right? Therefore, LEB of this z in the x1, x2 of dfz minus identity will be less than or equal to half, because each one of them is less than half, right? You follow that? Therefore, what do I have? I have fx1 minus fx2, assuming they are equal, minus x1 minus x2, okay, is less than or equal to half times norm of x1 minus x2. Okay, this implies x1 equal to x2. Yeah. So what have we shown? Now we have found an open ball BAR, so that the function f is 1, 1 on BAR. That's all we had achieved. But it is under the added assumption the derivative f at A is identity. As a linear map, it's identity, or as a matrix, it's a identity matrix. Yeah, is that a problem? Okay, let us do that. Suppose d of A is A, assume non-singular, right? Now let's look at the function g, which is A inverse of f. G of x equal to A inverse of fx. Do you follow that? Remember, now A is a fixed matrix, right? It will be del f by del xj at A, but this is now A is fixed, therefore this is a constant matrix. Okay, matrix consists of real numbers. Okay, this is, do you follow that? Okay, therefore this is my G is A inverse composite f. Do I agree with that? Okay. Now notice that since A is non-singular, A is a bijection, right? So if I prove G is a bijection, that is G is 1, 1, and since A is 1, 1, should it imply F is 1, 1? If I say G is 1, 1 on some BAR, does it imply F is 1, 1 on BAR? Suppose I prove that. Yeah, that's clear. Why? Because my F, where do I get my F? F is A composite G, right? A composite G, right? G is 1, 1, therefore fx1 equal to A of gx1 and F equal to A of gx2 equal to F of x2. Suppose fx1 equal to fx2, what does that mean? A gx1 equal to A gx2, but remember A is bijection, therefore that means gx1 equal to gx2, right? But then G is 1, 1 on BAR, therefore that means x1 equal to x2. You follow that? Therefore it's enough if I prove G, there is an R positive, so that G is 1, 1 on BAR, right? But that's very easy. Now let's look at G. What is G? G is a composite of F. Now F is C1 and A is actually C infinity. Any linear map is, remember A, this linear map is A on X. Okay, it will be A1 x1 or A11 x1 plus A1n xn and AN1 x1 plus AN1 x1. So each of the coefficients are first degree polynomial, therefore they are actually C infinity. Therefore the composite is C1. And what is the derivative? And what is the derivative of G at A? By chain rule, it is A at F of A. Sorry, I wanted A inverse. I'm sorry. A inverse, but A inverse also a matrix, whatever I said. Any linear map is infinity, therefore A inverse is C linear map, therefore it's also C infinity, therefore the composite is human. A inverse of at FA, right? And composite DFA. But what is DFA? It is A. But what is the derivative of, remember, this is derivative of the map A inverse, but this is nothing other than for any linear map the derivatives itself, therefore it's A inverse itself, because A inverse is the map. Please don't get confused. A inverse is a linear map from Rn to Rn, right? Therefore the derivative of A inverse at any point x is A inverse. This is one of the this we did in our second lecture on several variable calculus, right? That is identity. You follow that? Therefore G satisfies all the properties I needed. That is, dg at A is non-singular, it's identity, and G is C1. Therefore what do I know? There exists an R positive such that G is 1 1 on BR. By whatever I said from that, it follows F is 1 1 on BR. Do you follow that? So we have proved, okay, there exists an open ball on which the function F is 1 1. So what is our assumption on F? F is C1 and the derivative at A is non-singular, or the Jacobian matrix is invertible. Under that assumption we proved this. Okay, review this, go back and go through this. In the second lecture we shall look at the second step, namely the openness of the map. Okay, and that proof will be very, very interesting proof. Okay, whatever you learned in the last few lectures of mine on calculus of several variables, okay, we will use them. You will enjoy the proof, I'm sure. Okay, have a good day, take care, stay safe, we will meet again.